Let's go back to Schrodinger, the non-relativistic Schrodinger equation. Let's think about the one-dimensional prism, so a particle that's forced to live between x equals 0 and x equals L, as a way of getting some sense of what has now changed when we introduce relativity into the picture. So maybe this can give us some sense of what the problems are that we are now going to face. So let's think about we solved the Schrodinger equation and we got these functions which look like this. Right, these are the eigenfunctions of the one-dimensional prism. And so the solutions come in the form of superpositions, right? These are discrete functions, discrete waves, so we sum over waves to describe the particle with coefficients, Cn, sine L, and then we have the time-dependent term, I-E-N-T over h bar. We haven't written down the E-N's, but we just want to get a sense of the general structure. And let's remind ourselves that this is a solution to an equation that looks like this. Right, where this is the Hamiltonian operator. And basically this is telling us that the rate at which the wave function changes everywhere in time depends on the energy. So this is, maybe we should write this. This is, so the Schrodinger picture has the wave function changing everywhere in time according to this prescription. This is in opposition to, so it's in opposition to the wave function evolving in time at some location, so at some location such that evolution in time at another location is compatible with relativity. Okay, so it looks like this prescription violates causality, special relativistic causality. So maybe we can get a more specific example of this. So let's think about solutions of this kind of thing. So we looked, in the quantum course, we looked specifically at a superposition that involved equal weights for the ground state, so psi 1 of x, e to the minus I, e1t over h bar, plus psi 2 of x, e to the minus I, e2t over h bar. And we we constructed a probability density, P, and we drew it. So this is 0 and this is L. And at t equals 0, we found that function to be something that was like this. And then it came down like this. Went up and then came down like that. And then at a different time, we had a symmetry here, a symmetric situation where the function, I'm trying to draw the same thing, just flipped by an axis that's at L over 2 here. So we go up like this, come down like that, something like that. So this is at t equals 0, and this turned out to be at a time which is pi h bar over 3 times the energy E1. And So we have a particle who has a large probability of being found somewhere here, and then at that time has the same large probability of being found over here. So, but what if we have a situation where L is much greater than c times t, where the time is now pi h bar over 3 e1. Well, what if we have that situation? Then what we have is that the probability is increasing near L, despite light not having time to get there. So that seems to be very strange. It seems to be violating the principles of relativity. So now we have the solutions to the Klein-Gordon equation, right? And they look like these kinds of things, right? They are e to the I kr omega t, but we have plus and minus solutions to this. And that's certainly different from just this kind of thing where we only have positive frequencies emerging. So as a result of the second derivative in time, we get the positive and negative ones. So maybe in this kind of object, we have a solution to these kinds of issues, but we need to deal with the negative energies, the negative probabilities, and the probability in time evolution of the probability density that we noticed in a lecture or two ago exists. But this kind of thing is the only difference, and so we might want to use that to solve all these problems.